And one way to think about it is as the coefficient improvement type of procedure, but tailored towards convex nonlinear functions rather than just some linear functions. Uh, and another view is to view it in the more general framework of disjunctive programming, where you have some union of sets. So let me give you an example. Suppose we have some binary variable y1 which takes values 1 or 0, and we want to model two different situations depending on what y1 does. Okay, so if some switch is on, one process may run, or some, we are in certain region, and if y1 is 0, then we are in some other region. Okay, so so let us say that in this, when y1 is 1, I want to be satisfying some inequality, let's say x1 square plus x2 square by 4 less than equal to 1. Okay, and when I am when y1 is 0, then I may want to satisfy some other inequality, maybe x1 square by 4 plus x2 square less than equal to 1. Okay, so one way to model it is using big M's. Okay, so can we quickly write how we can use y1 to model these two conditions? So I will just add, so I will have two constraints, both these constraints, and I will add one big M times 1 minus y1. Okay, so as soon as y1 becomes 1, this term vanishes and I'm left with this, and similarly this would be some other big M, okay, not necessarily same y1. Okay, and if you want, you can find biggest possible M's and try to make it as tight as possible. So this would be your coefficient improvement type of thing that we talked about in the previous class. Okay, but this doesn't give you really the convex hull. Okay, and I will give you an example later. Okay, geometrically, what type of a region is this? Some ellipse. Okay, so let's try to draw this. Okay, so this axis I will keep as z. Okay, not z, y1, all right, the integer variable. Okay, so that means there will be two points of interest where y1 is 0 and y1 equal to 1. Okay, so at y1 equal to 0, I want this to be true. Okay, so so this will be an ellipse something like this, and at y1 equal to 1, it might be an ellipse which is elongated in the other direction coming out of the board, and thinner in the other one. Okay, so let us say something like this, it looks like. Okay, okay, so if I want to find the convex hull of, where are the feasible points? The feasible points are everything inside this ellipse and everything inside this ellipse. Okay, so this ellipse is one axis is x1 and the other is x2. So since this is longer here, so I will say this is x2 and x1 is coming out of the board. Okay, so this ellipse is like this. Okay, and then there is a different ellipse here. Okay, so if you really want the convex hull of all the feasible points here and all the feasible points here put together, okay, so then you need some sort of an envelope over this. Okay, so this should progressively go down and something like this. So it will look like some odd shaped bucket, okay, which has very straight edges, tapering down towards going into the shape of that ellipse. Okay, so the convex hull is this 3D object, all right. Yeah.
The second one is the coefficient of x1 squared 4 is the 1 quarter. Otherwise, the ellipses don't have the same. Don't have the same eigenvalues.
Yeah, they don't. I mean, they are two distinct convex bodies. They don't necessarily have to be scaled versions of each other. Okay. If they are scaled versions of each other, then it is even simpler to draw. But in general, these don't have to be scaled versions of each other. Okay. So so one way is to come up with some sort of a method to find what is the convex hull. Okay, and this is usually treated in the area of this thing called disjunctive programming. Okay, where you have two distinct sets and you say what is the union of them. Okay, so I want to be either here or here. I don't want to be elsewhere. So then how do I represent it as tightly as possible? Okay, so this is called disjunctive programming. Or okay, and there is some work by Stubbs and Mehrotra and some other, including Balash, on how to find the convex hull of such distinct objects. Okay, it turns out that you need extra variables. So you make, instead of having the same variables in both sets, you call these as x, call these as w, and then take some convex combinations of those variables. Okay. Things get little simpler when one of the sets is sort of just a point or a small line segment, and the second set is some convex shape. Okay, so there this the simplified version of this disjunctive programming can be understood in a better fashion. So here is an example. Suppose the extreme case of that is when at y1 equal to 0, I just have one point, say that x1 and x2 both are 0, and when y1 is 1, I have some ellipsoid or some other convex shape. Okay. So then the convex hull is actually sort of some cone which starts at this origin and spreads towards this convex body and encloses it in some ways. Okay, so in 3D you can imagine. Okay, so if you write it using some big M notation and all, it won't be this tight. It would be it would be looser than this. Okay, and we would like to find what is the reformulation for this set, so that I get the convex hull. Okay, so let me start with a numerical example so that we can understand it better. Okay, so the simple object that I will take is not really ellipse, but a even simpler thing, a parabola. Uh, so the set I am looking at is x2 greater than equal to x1 square, and a indicator variable uh, which turns off x1. Okay, so I have x1 less than equal to y1 0. Okay, so I have an indicator variable only on x1 which is y, and y is binary. So when y1 is 0, x1 becomes 0, and x2 is allowed to take any value more than 0. Okay, and when y1 is 1, then x1 can take any value between 0 and 1, and I have a parabola between 0 and 1. Okay. All right. So uh, at y1 equal to 1, I have this feasible region, and between 1. Okay, so this picture is when y1 equal to 1, and when y1 equal to 0, I just have a line where x2 is more than 0. Okay, so y1 equal to 0, and this point is x1 equal to 0, x2 equal to 0. Okay, and here x2 is increasing. All right, and the result is that if you rewrite this set, okay, so let's say this is set S1. If I change this set slightly and change my nonlinear constraint to x2 square greater than equal to x1 square by y1. Okay, that doesn't look very good because y1 can take 0 values, but so what we can do is take y1 to the other side. Okay, and if I look at this set, all right, these two sets are same. All right, first claim is that. Okay, why are they same? Because when y1 is 0, x2 can take any value. All right, but x1 can take only 0. Okay, same as here. And when y1 is 1, I get my original constraint back. Okay, this one. All right, so S1 is equal to S2. Okay. Is this a convex Minello? Yes. Why? Because this is some convex function, and I am saying that x2 must be more than some convex function. So above it is a convex set, and these are linear. Okay. Is this a convex set? Why not? Because we have some bilinear term here, and in general this function is not convex. Okay. But if I write it as x2 greater than equal to x1 square plus y1, it is actually a convex function. Okay, this constraint is convex. X1 square by y1. Okay, provided y1 is slightly away from 0. Okay, so I can redefine this function slightly, and so it will turn out that this is also actually the set of feasible points in the relaxation is a convex set, even though it may not look like a convex set right now. Okay. The other claim is that if I change this to y1 between 1 and 0, and so that means I am looking at the continuous relaxation of these two sets. Okay, so R1 is where I have relaxed this, and R2 is where I have relaxed this. So then one can easily show that R2 is actually a subset of R1. Okay, so as far as we are looking at integer values of y, these two sets are same. Okay, but for non-integer values of y, fractional values of y, we have this relation. Okay, so can we see why that is true? First of all, so this is my original constraint, this first half, and I am multiplying this with something smaller than 1. Okay, so or the other way is that if I take it to the other side, I am dividing it by something smaller than 1. That means I am increasing the right hand side by, and that means if I say x2 is bigger than some bigger number, then that set is smaller. Okay, so it's a very simple logic. Since I am multiplying this part with something smaller than 1, the feasible region is actually smaller. Okay. Simply because y1 x2 is less than equal to x2. Okay. Also there are points which are in R1 but not R2. So let's take a point, say y1 equal to half. Okay. What happens at y1 equal to half? I am allowed to take the value of x1 as half. Okay. So x1 equal to half and x2 equal to 1 by 4. Okay, so this point belongs to R1. Okay, this is a feasible point of this when y is allowed to be fractional. Okay, does it satisfy these constraints here? This is not satisfied because this side becomes 1 by 8 while this is 1 by 4. Okay, so this side is 1 by 8, this is 1 by 4, and clearly it is not violated. Okay, so so that means this is a weaker formulation, this is a stronger formulation. Okay, and the the result from perspective says that it is actually the strongest possible formulations. It is the convex hull of this set. Okay. So there are two things I want to talk about. One is why is it called a perspective reformulation? Because it is related to something called a perspective of a function. Okay, so that is a mathematical term. So if f is a convex function, okay, let f x be a convex function, then its perspective let's say I'll assume a little bit more. So I will say with f0 equal to 0, okay, then its perspective with respect to a variable t is defined as t times f x by t. Okay. Is also a convex function. Okay. Of course, the difficulty arises when t is 0. Okay, so we have to carefully say what is happening at 0. Okay, so usually we say that so the usually the statement usually is that this perspective function, let's say f tilde of, so now it is a function of two variables, not just one way. I have added one more variable from my side. This is defined as t times f of x upon t for t not equal to 0 and 0 when t equal to 0. Okay. So if you define the function like this, then those difficulties diminish. And remember that we have assumed that f0 is 0. Okay. So it sort of remains continuous, okay, if you think about it. Okay. And it can be shown that this function is actually convex. Okay, so that is the main result from convexity analysis, that if this f is convex, then this function is also convex. Okay. The reason it is called a perspective is because it is, you can imagine this function as a view of the function through some pinhole camera, where as you go further and further away or change the distance, the image shrinks at a nice scale depending on how far you are. So if you have some function and you look at it from a distance, then it will look the same shape but smaller and smaller and smaller, and it will converge to some point. Okay, so or you can think of a source of light from which the light is spreading out in a cone, and you put the picture of some function. So as you go further and further away, the function keeps looking bigger and bigger, and the shape remains the same, but the size keeps increasing. Okay, and that is linear in t. So the distance you go. Okay. All right. So this is very much the case here, because at y1 equal to 0, your function is just one part of a line, and as you go further and further away, it starts expanding and at y equal to 1 it becomes this shape. Okay.
What do you mean by f of x by t? X is a vector.
X is a vector. So what is x by t? It is, and t is a single variable. Okay, so this is same as every variable divided by that t, x1 by t, x2 by t, xk by t. Okay. All right. Oh. Okay, so if I apply this theorem to this particular constraint, so here fx is x1 square, and if I apply the perspective to this, okay, so it would become, so if my fx is x1 square, that f tilde xt will have the form t times x1 square by t square. Okay, so exactly x1 square by y1. Okay. So this is a convex function in x and t. Okay. And the other part is that if we replace this function by this one, it still looks the same at integer points, but at the other point it is tightened up. Okay, and this is the best possible you can do. There is a proof which says that you actually get the convex hull of this disjunction. This plus this will give you this. Okay. I quickly want to show this, or maybe we are running out of time a little bit in the tutorial. After 10 minutes, I'll show you some picture of how it looks in 3 dimensions and which parts are actually chopped off. Okay, once I open my computer. Okay, so so this can be applied to other nonlinear functions also. For example, if I have a function like say 10 minus log of let's say 1 plus x1, okay, less than equal to some other variable x2. Okay, so this is a convex constraint. Okay, because the log function looks like this. Okay, and and we are, if it goes this side, then we are trying to be below this function. Okay, so we are here somewhere. Okay, so this is a convex. The description of this is a convex set. Okay, and we can apply, if there is an indicator variable on x1. Okay, so if there is something other way around, then I can apply this perspective transformation to this. But unlike the quadratic case, here I will not be able to cross multiply and take that near 0 y to the other side. Okay, that is not possible in these functions. Okay, so so it is still possible to rewrite this using perspective reformulation. The only issue is that so this is your f, so this would become t times or y1 times log of 1 plus x1 by y1. Okay, and if you give it to some nonlinear solver, continuous relaxation, if you want to solve, it will face difficulties because it would say I can't divide by y1 or something. Okay, so so what people try to do is take a small approximation to this transformation. Okay, by using some slight epsilons here and there. So one such formula is this, that so if we have g1x less than equal to 0, and I don't want to apply this transformation that y1 times g1 x by y1 is less than equal to 0, and I am not able to cross multiply this because it is not a polynomial or some other simple function. Instead of this transformation, we just perturb it slightly so that some of the difficulties go away. So for example, I can write it as y1 plus epsilon times g of it's a slightly complicated thing, but z this is y plus epsilon times some constant x hat here. This is obviously for one-dimensional variable divided by y1 plus epsilon. Okay, so you add some term to the denominator so that it doesn't really become 0, and at y equal to 1 it still remains exact. So some epsilons you add and take care of that. Okay, so the idea here is that instead of having a cone like this, with numerical difficulties here because things going to 0, you add a little bit to it in some ways. Either you add it like this, okay, this epsilon bit here, or you sort of round it up here, epsilon bit, and make sure that nonlinear solvers are somewhat satisfied and still able to solve and give you KKT points and such. Okay. Also adding linearization cuts at this point are tricky, but at other points you can still add. Okay. So tomorrow there might be one session where we talk about perspective inequalities for some very structured sets. So they tend to have real good impact for many problems, particularly this portfolio optimization and some other transportation type of problems. So with that, I will stop. I'll try to show you a graphic in the tutorial later. Okay.